Okay, so we have this problem from the 2018 F equals M exam A, since they started splitting it up into two. And this is problem 24. So mass is attached to one end of a rigid rod, while the other end of the rod is attached to a fixed horizontal axle. Initially, the mass hangs at the end of the rod, and the rod is vertical. The mass is given an initial kinetic energy K. If K is very small, the mass behaves like a pendulum, performing small angle oscillations with period t0. As K is increased, the period of the motion of the mass, A, remains the same, B increases, approaching a finite constant, C decreases, approaching a finite non-zero constant, D decreases, approaching zero, E initially increases, then decreases. Okay, so to tackle this problem, let's see what we need to know. So what we're trying to find for this problem is the period. So immediately what you think of is the formula for period, which most people know as this, but if you've taken the F equals ma, you know that this is an approximation, and really it depends on the initial angle a little bit, like very little, like angle squared over 16, where angles in radians, like very small difference for small angles, so people typically just don't think about it. So from here, you would think if you start with the higher kinetic energy, that's the same as, well, if you left a pendulum up here, it'd have some gravitational potential, which would turn into kinetic. So it's the same as leaving it up here and then having it go down and let it swing. So if you have an increased kinetic energy, then initially it's going to be higher up if it was started from rest. So this is the theta angle we're finding. So it gets bigger as the kinetic energy is increased. So that would lead us to think that, well, the period has to increase now. T goes up as kinetic energy goes up. But then, well, let's first get rid of our choices, which is always a good thing to do if you're unsure about a problem. Okay, so we know starting off for small kinetic energies, it definitely doesn't remain the same because it's the same as increasing the angle. It could be increasing and approaching a finite constant. It's not decreasing the whole time as the angle is going up. It's not decreasing, approaching zero. So it's either B or E. So you already have a good guess if you were actually taking the test and you don't know. Okay, but we've been leaving out a case here. So what about the case where there's enough kinetic energy down here to get it all the way and then have it just go in a circle and go in a circle and go in a circle over and over again? That also can be used by this. So that's fine. But what if when it gets pushed here, it also has some velocity up here that's almost comparable to this in terms of its magnitude? Because we know it loses a little bit of kinetic energy when it goes up because it gets turned into gravitational potential. But if we just load it with so much kinetic energy that this is about the same as the bottom, then this will be the same as a uniform circular motion, which is why I wrote this down, which is where you find the period of something given its velocity. So as the velocity is increased, and the top is almost, just barely, what the bottom is, we can say it could be modeled pretty well with this, which means the period is proportional to 1 over the velocity. And since the kinetic energy is proportional to the velocity squared, we know that as the kinetic energy is increased, that means the period must decrease, which makes sense because if you pushed it really fast on the bottom, then it would start spinning really, really, really fast. So that means the period must be decreasing. That must mean it doesn't keep increasing as you go on, meaning that it's E. It initially increases, and then it begins to decrease again. So yeah, that shows us that the period first starts increasing and decreasing.